Yeah. Sorry, I didn't open the microphone. So yes, I was saying I'm assistant professor in KU Leuven, Department of Mechanical Engineering, and I'm in this talk I want to introduce some of the topics of my group, and it's fine. So I mostly focus on digital twins for production systems, mostly for production planning and control applications. And today I'm going to introduce some of these topics. Pardon, I always like to start with a little bit of context. So we are all quite aware that recently several countries, continents are increasingly competing one another, and especially in Europe, we have, you might be already aware that we have discussions on how to maintain a high level of competitiveness. So there is a discussion over the obsolescence of some manufacturing systems, of some production systems, on the economic viability of systems, and at the same time, several external factors that we need to cope with, such as the rise of raw material prices, energy prices, and skills shortage that is very common in the industrial sector. So, like it or not, I think competitive times are ahead. So we will need to cope with this situation. So we can expect that companies will invest and strive to remain competitive in the near future. At the same time, we are also quite lucky that we come from, in the last decade, we had the fourth industrial revolution, right? So in the last decade, there's been a lot of investments in automation, a lot of investments in data analytics, IoT, and data elaboration capabilities. And we can expect, we can see also from some figures, we can expect these numbers to continue to rise. I took some figures from the World Manufacturing Foundation, the report of this year. So you can see that we can expect the digital transformation to continue and to continue even more rapidly than before. And we know that for most businesses, the impact of the digitization has come mostly from the application of IoT and AI. So these are very prominent technologies. And we also know that one of the most cited technology that we are also well aware of today are digital twins. And just to give a bit of introduction, we already saw quite a bit on digital twins, but I also took some figures that contextualize a bit better. So the manufacturing is predicted to be the biggest sector where the big digital twins are to be applied. So there are some predictions on that. And there's a vast majority of companies that consider the digital twins as a crucial solution to their strategy. And yeah, we can already see even from popular news channels that digital twins are becoming also more well known, so to say. So just to give a bit of context again, we have several types of digital twins possible. This is taken from our tutorial paper from the Winter Simulation Conference of last year. So we can classify digital twins in different ways. I don't claim this is the most complete way, but just to be aware that depending on which type of system we twin, there might be different implications and different features in which we are interested. So we can make a digital twin of a product, which is probably the initial digital twins were coming from this type of an environment. So we can twin, for example, there is projects on the digital twin for the buildings, so the context of civil engineering, biological, so for example, for plants or fish farms. and we can make a digital twin of a system. So today I'm going to focus on this case, in the upper right case. So the digital replica will mirror a complex system, which is a collection of parts that are organized for some purpose. So let's remember this, this part. And I tried to summarize in a slide what I try to conceptually visualize the life cycle of a digital twin for a manufacturing system. Of course, this is purposely simplified a bit. So we have on the lower side a physical system, and we have data collected from the system. And digital models are replicating the behavior of a system. We can use several types of digital models, so this is not necessarily restrictive. So it can be a simulation model, but it can also be an analytical model or data models and so on. These models are used to provide some sort of services, so what I call external services. So planning, predictions, performance evaluations, or some sort of rescheduling and replanning services. My claim, or the claim of our research in the last years, is that the reliability of the digital twin is dependent on the harmony between the external services and the internal services. So what I call internal services are some applications or methods that the final users will not necessarily see, but they will need to be there in order to preserve the capability of a digital twin to perform the services and to have up-to-date models and to have a correct level of alignment with the physical system and to have valid models. So to be able to perform correct predictions. So today I'm going to focus on three major topics. So to show topics that I'm working on, the model generation. So how can we focus on using data to create models that are up to date and aligned with the physical system. Online validation. So how can we make sure that these models that are very dynamically changing, since they are generated from data and the system are changing too, so they keep changing and they need to be valid all the time. How can we do it also in an online manner? Then I focus a bit also on the rescheduling, rebalancing, and so some external services indeed that can be designed thanks to the digital twin framework. So, for example, services that that react to some triggers, some events in the system, and provide a reaction strategy or a prescription to the real system. Okay, so let's start with the first topic, model generation. So how do we? Why did we start to work on this topic? So if we take a system here on the lower side, we know that modern manufacturing systems, production systems, are very dynamic. So they can change not only in their structure, but they can also change in their logic. And this happens with a very much higher frequency than before. So we can have the addition of resources or the change of production routings, the change of maintenance policies, the change of operators allocations, and so on and so forth, of course. You can imagine several situations. And if we have digital models, simulation models that are designed for typically at the design stage of the system, if we don't have if we have this situation of a dynamic system, it's very hard to conceive a situation in which the digital model is continuously updated in a manual manner. So we need more automated approaches to be able to follow the behavior of the system. And of course, also correlated to what I've said, like we have a lot of data collection devices that we can reasonably assume that they are more and more in place. So we can use, the intuition is if we can use data to generate models, then we could achieve a much closer alignment a long time, and to be able to update the models in a much faster and shorter term. So what do I mean by models? In this part, I focus on simulation models, specifically discrete event simulation models. So they are models that are very commonly used for modeling the material flows in a complex system. And we know from the literature that graph models, such as Petri nets or directed graphs, can be used to represent the basic logic, the main logical element of a simulation model. So a graph is a mathematical representation of any simulation model, can be the mathematical representation of any simulation model with any level of complexities. There are nice papers from Professor Schruben that I could reference to you. So we looked at, when we started this research, we looked at the literature, looking for methods that were able to generate graph models. And process mining, of course, maybe some of you are familiar with this technique. Process mining is a technique or a collection of techniques that addresses the need to use data sources from a system and generate models. So in this case, the flow discovery is generating graph models in which we mostly have directed graph as the first output, but we also generate Petri nets with many algorithms. And basically, they represent the main relationships between events that occur in a system. So we started from here. And then we tried to develop algorithms that were overcoming the limitations of process mining when applied to manufacturing systems. Why? Because the most process mining applications were developed for business processes and for other applications, mostly relating to a single case or relating to the series of events that a single case had to handle in a system. But they were less prepared for systems that had to manage multiple flows of material and, for example, finite capacity of resources, which are two major characteristics of manufacturing systems. But let's take a moment also to understand a bit better this. So if you allow me to oversimplify just a little bit, then we can all understand what it means to generate a model starting from data of a manufacturing system. So imagine we have a two-station of a manufacturing system, production system with two stations, and in between we have a queue. And we can reasonably assume that the flow of parts between these two stations will be tracked. This is typically a typical feature of manufacturing system because most of parts have QR codes, data matrix, and or barcodes, so they are typically tracked at significant points of production. So we can reasonably assume that we will have at least a few information types. So we will have we will track where each part has passed in which station and at what time. So these three major information types that we can summarize them in what is called in the process mining literature event log. And okay, starting from the log, so we can follow since we know the time at which where each part was in which station, we can then already generate our first graph model in which the nodes are the activities or the stations in this case, and the arcs are the material flow information. So that, for example, an arc from from node 1 to node 2 will represent a flow of material from station 1 to station 2. And okay, this is already possible with process mining. What do we miss, for example, in a manufacturing case? So if we have a queue, which is also another common situation, parts can accumulate from between the two stations. They're also common. And we know that the buffer size is very relevant for the capability of the model to estimate the performance of the system. So we can use again the log to infer the buffer capacity by simply looking at how many parts were accumulating between these two stations from the log. And there we have a first addition, a first enrichment of this graph that is, for example, can be expressed by the property of an arc. So, for example, here we have 3 parts accumulated, so we can infer the buffer capacity is at least 3 parts. So you see that by enriching the model, we can then translate our graph model to a simulation, and then we can actually populate our digital twin. Okay, just to give you an idea of another major issue that we need to solve specifically for manufacturing is that if we simply apply process mining techniques, we might end up with over complex models. So here, for example, is a figure of a typical model that can be generated with a common number of sensors in a system. What we typically do as modelers, when we go to a factory, we observe the behaviors of the factory. We then actually abstract information, and we decide which parts of the factory to model, which parts of the system are mostly more impactful, and so on. So we actually tune the level of detail of the model, and we go from a very complex to a more simplified, but it's controlled, this simplification. So the general idea is that we want to simplify the model level of detail, but we want to control it at least. And if you think about it, it's something we do it almost every day. So imagine when we use maps, we do decide which level of detail of the map depending on our intended application, right? So if I need to move around Paris, this is I will use a map of all the roads, right? And I see all the detailed roads. But if I need to move from coming from Brussels to Paris, for example, I will just be interested in the major railroads or highways, depending on which mean I will use, right? So, okay, so this is the idea of the tuning. So we want to find the model with the minimum size that maximizes a sort of utility, a score. So we need to define these two parts. So how did we do this? Again, allow me to oversimplify a bit to just convey the general idea. If we look at the system, for example, we have here a system that where materials are flowing inside a robotic cell, and we can infer that actually the robotic cell might be just one element of our model, because we know that in a robotic cell, events follow one another in a quite deterministic way. And we are just, as modelers in a simulation, discrete event simulation, we would typically just model the time that the parts spend in the robotic cell. So if we imagine, of course, in the robotic cell, we might have a lot of sensors, a lot of events happening, but we are interested in aggregating these events because we want to just have a station there. We want our model to be simple, not to be overcomplicated because we have several robots inside here. So we can see, we can try to notice some properties of the events in the cell. So for example, the fact that they will be reasonably very close one another, or the cadency of the events will be very similar because they are deterministic. So we need to recognize some properties, and then we use this property as a driver for the simplification of the model. So for example, here if we have 3 nodes, we use this score that is the property, this property score. So we see that between the second and third node, there are more events with this property of being close one another, for example. So then we use this driver to simplify the model. So this will be, following this logic, will be the simplified the best model to simplify. So we will use this as a decision maker to merge the last two nodes. And we have a cluster, and this is our robotic cell finally. And we applied this logic. Of course, I would refer to the paper if you're interested in how the whole algorithm works. We applied this to a real case. Was a real case from industry of electrical engines in Italy at the time, and we took a log from the company that gave us a log of a part of the system. And the nice thing is that we were able to generate the graph model with all the properties, and then tune the digital model. And the interesting part here is that the nodes that were aggregated, they were exactly corresponding to what this was a conceptual view from the company, but they were exactly corresponding to the choices of the modeling choices of the company, because we knew that some events were redundant, and so we oversimplified in the same way that we simplified in the same way that the model would that the modeler would do. Okay, so how are we continuing this work? I'm showing more. This is more current work. So we are now able to generate graph models that will become simulation models. We are now trying to add information on the system state, because the current state of the system might actually also be relevant for example, a reaction policy, or to design to reschedule the production, for example. And we want this to be visible in the model we generate, so we can use the model at potentially any time to then design reaction policies. And at the same time, we want to also have a certain level of fidelity in the reproduction of the production policies. For example, if I have a queue, there are dispatching policies that decide in which way we load or unload parts from the queue, typically FIFO or LIFO policies. And we want also this to be correctly represented in the model. Okay, so here are just preliminary results that basically that this is the joint work with Polimi at the moment, so basically with different types of systems, we are trying to see, okay, with enough data, we are able to reproduce properties of the system that, of course, depending on, so with more and more data, we are closer to the real property of the system. So, for example, a buffer size, or a routing policy, for example. Okay. Okay, great. So we finished the first. This is to give you an idea of the first current work. I move to the second topic. Again, remember the whole picture. We are now talking of internal services, so something the user will not necessarily see, but it's a way to keep our digital twin alive and keep our digital twin reliable for its scope. And the second topic, we focus on validation. Validation is typically divided into two main categories. So we focus on, we can have both logic and input validation. So in this work, we focus on input validation, which means are we correctly modeling the input data for our model. So for example, again, if we take a real system on the lower side and a digital model on the upper side, here we have a simple closed loop system of two stations. What we typically are interested in the validation is that are the parameters. So I have, for example, a distribution that is modeling the processing time of a station. And of course, I want this to be very reliably reproduced in the digital model. And of course, if the system changes due to some disruptions or due to some problems in the real system, we might have actually a deviation. And so we have something that might not be reproduced in the digital model. And we need to be able to recognize the situation. This is typically reflected in the model output. And in the traditional approaches, this is recognized in if we take the real and digital KPIs, we will typically take aggregated measures over a long term. So if we take we take a very long horizon of our simulation, and we will typically see it. But this goes against our assumption that we are trying to cope with dynamic systems. So if the system changes very rapidly, we might not have enough time to recognize the deviation. We might not have enough data to take an historical data and to compare the two measures. So we need a more dynamic way to do this. And recently we developed a technique that is basically based on some techniques from the literature, such as dynamic time warping or the comparison of sequences for example, comparing DNA structures. And basically, we are comparing the sequence of data coming from the shop floor, so the real system, and the digital twin, the digital model in the digital twin. For example, inter-departure times from a station, a very common measure related to the throughput of a system. And we basically take this data. We need some correlation in between to be able to compare the data. And we create a similarity indicator. So a measurement that tell us, okay, how close is the digital model to the real system. And this indicator can change each time we have a new data point from the real system. We can also generate one in the digital model, and we can always update the indicator. So, of course, I refer you to the paper for the whole technique. But basically, here are some preliminary experiments that are also shown in the paper. So basically, what are we doing? We take two simple systems, a queue and a server. For example, a GG1 queue is a very typical, very typical system in the literature. And we take a KPI of interest, and we use our technique to compare. So every time a new part is produced, we update our indicator. And here we can see like the cases in which, so basically we take, this is done in the digital to digital scenario. So we just do this entirely digital. And basically we take the case of two identical systems, and we create our indicators. And of course, in this case, the indicator is very high, because of course we see that the two systems are identical, and this gives us an indicator of the upper bound. And we can already also see that the fact that it's not 100% immediately because of noise. Of course, we have some noise at the beginning. And then we change the parameters of the digital model, and we see how our indicator is behaving. And we see that all curves are dominated by the blue curve. So we already see that we are always able, even with small deviations, we are always able to detect with small deviations and with a few data points, we are always able to detect the deviation. And this, we also tested this in a real to digital scenario. So we didn't have a factory, so we built one ourselves. There is more details on this in other papers, of course. But basically what we take again is a physical system with some characteristics. And then we apply a disruption ourselves. We talked a bit this morning. We need to be able to apply disruptions in systems, and so to study this behavior. So this is something we have done as well. We apply a disruption, and then we will use then, we are interested to use the digital twin to be able to decide between different scenarios. So for example, do we repair this machine or we don't repair it? So this was the general setting for the digital twin. But of course, before we can do this, so use the digital twin for the scenario analysis, we need to be sure that the digital model is valid. So we apply our technique in this case. So basically, we start operating the system, and we apply at a certain moment, we will apply the disruption. So of course we can start our indicator even before we apply the disruption, and we can verify our indicator is collecting data online and generating also data from the digital twin. And we see the fact that, okay, at the beginning we have a reliable digital twin, a valid digital model. And then after we apply the disruption, we see that our indicator starts to go down, and we finally end up in a warning and non-valid zone. Finally, we need to modify our model before being used for what-if analysis. So we use data to fit new distributions, and we update our digital model. So, and this is visible on the last video. So we see that after we do this, we also can have a measure that our digital model has gone back to valid. So, okay, so this is a bit out of scope for today, but basically just to show you the whole demo, basically, okay, after we have a valid model, of course, we can use what-if analysis and decide what to do in the real system. So we decide in this case to repair the machine, and we would implement this. And now current work is to extend this framework for validation. So basically, this is just conceptual because I don't have much results yet to show. But basically, we're trying to extend not only for the input data model case, but also for other types of behaviors that need to match between the digital, between the real and the digital. So we are trying to also recognize the fact that the dispatching policies or production policies are aligned, or for example, the fact that an operator model is up to date and is valid. So this is also the goal is to achieve a greater, more complete framework. Okay, so I have little time left, but I will try to also cover the last topic. So in the last topic, we basically try to also use digital twins for, well, the main purpose is to apply some services to the real system, right? So we also address this case. And I just want to introduce you also some current projects. So this is a relatively big project in Leuven at the moment. If we take the whole budget, is around 1 million, so which is quite big for an internal project. And basically, we are this is already in place in the lab. We have a demanufacturing line, and the line is basically focusing on how do we disassemble electronic materials such as common electronic such as phones and screwdrivers, or that can also be laptops or battery packs for bicycles, for example. And the line has different stations. We have both manual and automated stations. And so the idea is that we will have a real system that has several decision points. So for example, after we detect in the first station, which in the lab would be this one, after we detect the product, then we need to take some decisions. So for example, do we unscrew the screws in an automated unscrewing station, or do we simply send it to a water jet station to be cut, for example, if we have some parts and so on. And this is not the only decision. We need to also, for example, decide if we have batteries, how many times do we test the batteries, or do we send a battery to scrap or not, and so on. So, and there are several services that we need to design, and at the moment we are working on this with a postdoc, and we started to identify the major challenges of this of designing these systems, and for example, the fact that demanufacturing has a higher complexity compared to typical manufacturing systems, because the variations of products is much higher. So the complexity of the automation process is also unprecedented, because basically each single product has can have we can steer the production potentially at each single product. So we need to, in my opinion, we need to even redefine what it means to plan the production in this type of systems, because probably we need another definition even. And okay, so finally also another type of project. This is closer to the traditional line balancing or line rebalancing, but it's fairly easy applicable also to the manufacturing system as the one I showed before. So basically here we are working, it's a collaboration with the Budapest University of Technology. We are working on a fairly traditional assembly line, so with 2 or 3 operators, but that is monitored by a camera system. And basically parts are recognized by a camera system. They are inserted in kits. This is from an industrial case, so it's a tier 1 automotive supplier, and the product is a valve. And basically, again, the idea is so we are able to retrieve which parts were assembled in each step. So we have data coming from the system, and the idea is that we will generate again our graph model. But in this case, the graph model doesn't represent only the logic of the system, but it will also represent the current balancing, the current solution for balancing the line. Because at the design stage, of course, we will have a nominal balancing solution, but during the production, some changes might be applied by the operators, for example, or they might be simply not. They might simply not follow the nominal processing time. So we need a system to monitor this. And then we will use this graph model to generate scenarios and generate alternative reaction policies to rebalance the line and to, of course, provide this information back to the operators. And so this is just to show you a bit how it looks like. So we have cameras on the kits, and basically the idea is that the cameras can detect when parts are assembled. So we are able to retrieve data from the assembly. So while operators, these are some tests, while operators put part and assemble part, we have a tracking system. So we are able to, again, remember the event log I showed you before. This is basically, again, retrieving events in the real system. And if you remember that, we would then generate graph model starting from there. And of course, this was applied. So again, the graph model is basically a directed graph, but inside each of this, we will have a more detailed view on the balancing. And actually, you can see some more details here. And we have used at the moment any logic and a connection with Python to show this the generated model, and then this will be used, of course, to analyze the scenarios. And this is currently a master thesis, so that we will. I hope to show you more results soon. So finally, we are moving toward higher automation of DTs, and so I want to find a connection with the talks before. I am not working much on the condition monitoring of a real system, but I monitor the digital twin. So I do maintenance of digital twins, so to say. And in the future, what are we expecting? So I took 2 slides from Michael Grease and my former supervisor Andrea that look a bit in a similar way how the future could look like. And they both send a similar message. So we will have more cohesion between digital models, and we will also need to find a way to have a coherence between models of different parts of a system. If we have a complex system, we will model different parts. We might have multiple digital twins of different parts. So finally, we will need to have what is now being called federations of twins, and of course, several interesting topics can be thought of from there. And of course, if you so as you know, I recently started, so I have funding for PhDs. So if you know anybody could be interested, I am promoting a bit myself, my group, that we will have open positions on several of these topics. Okay, almost on time.
Yeah, so thank you very much.
Okay.
Yeah,
Thank you.
Thank you for catching up a little bit. But I think we still have some time for one or two questions, right? So in the room or online. So if you want, we can.
I should move back.
Yes, Sophia.
Thank you very much for the very nice, interesting presentation. So I have the curiosity regarding the communication between digital to digital models, right? So you say that one of the digital models changes,
yeah.
so the indicator changes,
yeah.
and then you need to inform the
yeah.
other model. So can you explain a bit what is the exchange of information between the two models, and how exactly do you update, inform the two models?
Sure. So, so physical to digital, we have, of course, a collection of data. In the case of the lab, we have done it through a time series database, or we have time series data. This is material flow data, so the event and each station, of course. So this goes to the digital twin. Of course, there might be an aggregation step in between. So if we're, for example, in the simulation model, we have a distribution. So of course, in between we have a fitting, or we have simply a trace-driven case where we just feed the same data through and or
Giovanni,
correlated data.
Can you repeat the question?
Sorry, the question was sorry, I forgot. Yeah. Sorry, the question was a bit on how do we
we have a question.
How do we connect the digital to digital and real to digital data, right? So which type of data connectors are there? And of course, the way back is, so the real to digital is fairly traditional in a way. So saying that, okay, we do the same or similar steps as a modeler would do. So to extrapolate data and to feed the digital model with data. On the way back, we have, of course, a lot of more freedom because there's not a lot of formalized approaches. So, for example, in the case of the test or the demo in the lab, the idea was, okay, do we repair the machine or not? So we have a decision back in the system. And so that can be either a recommendation or, okay, in the lab, we can automate everything. So we did already a test with an automated response. And so in that case was implemented with IoT, so with MQTT specifically. But basically, the idea is we will send a message of the prescribed action. So that can maybe very shortly. Sorry, but if you're interested, I can show you the details.
And then also the question online. So sorry, okay, maybe it's the last question.
So I read it for the people here. For the graph model in your slides, how many types of nodes edges does it contain? How efficient and scalable the algorithm for processing this graph model? Okay, thank you. So I think it's talking about the tuning. So in the tuning test, so in the model adjustment algorithms, we used relatively simple cases. So with assembly lines or FMSs with between 6 and 10 stations, and of course you can have a bit more complexity because in each station you might have up to 10 and 20 events. We did not test. So in those cases I mentioned now, the computation time was still reasonable, so between 1 and 5 minutes. With the heuristic algorithm for the tuning. If you're interested, there's more details in the paper. For more complex systems, I don't exclude that this will become a challenge, but yes, I still didn't test the limits of the approach.
So if you have a budget, maybe you can support Giovanni.
Yes, we need computation. Exactly.
So there's another question, but can you just give a very quick?
Okay, thank you. For semi-automated, Well, at the moment we didn't tackle the semi-automated case, but thank you, it's very interesting. Maybe we can also, we need to speed up a bit here, so we can take also this. I see you're very interested, and so thank you for the interest, but maybe we can take this offline.
So maybe you can come, with your project proposal to Professor Giovanni.
Yes.